Welcome to this introduction video to quantum mechanics. In this video we will discuss a bit of history and what makes this field so mysterious, and why it remains mysterious even today. While the math of quantum mechanics is solid and well understood, the physical interpretation of the math remains unclear. As Niels Bohr himself said, if you're not confused by quantum mechanics, then you haven't really understood it. Or in the words of Richard Feynman, I think I can safely say that nobody understands quantum mechanics. Nevertheless, I will do my best to introduce you to this very interesting field of physics. First, we can start looking at a bit of history, as it is less mathematically complex and it helps us understand how things developed. The birth of quantum mechanics was at the beginning of the 20th century. At this time, Max Planck's research of blackbody radiation led him to the concept that energy was quantized according to the equation E equals to h nu, where E is one quantum of energy of some particle with frequency nu. H is Planck's constant, which turns out to be essential to quantum mechanics. In 1926, Erwin Schrödinger came up with possibly the most famous equation from quantum mechanics, namely the Schrödinger's equation. In the following decades, many famous scientists uncovered this new field, including Heisenberg with his uncertainty principle, which fundamentally changed our perception of the world. Quantum mechanics gave us a much deeper understanding of the subatomic level, and in the process gave us fundamental insight into the world of chemistry. To get a feel for quantum mechanics, it's important to get a feeling for quanta. When Planck found that energy was quantized, it means that energy comes in certain chunks of energy. This is fundamentally different to classical physics, where things are continuous, thus they do not come in these chunks. As the name quantum suggests, things in quantum mechanics are quantized. This means that photons, for example, have a discrete amount of energy which is directly linked to Planck's constant. This really helped explaining photon absorption and emission in atoms, as the energy levels are distinct. Planck's constant is seen in basically all equations in quantum mechanics, but it's often written slightly differently as the reduced Planck's constant, or h bar, which is defined as h bar is equal to h divided by 2 pi, which is roughly around 1 to 10 to the minus 34 joule second. Note that this number is extremely small, and this is part of the reason why we don't see any quantum effects in our classical world. Now let's move on to the Schrödinger equation, which is the first equation most university students meet in introductions to quantum mechanics. It is often written as minus h bar squared divided by 2m times the double derivative with respect to x of psi plus v times psi is equal to I h bar times the time derivative with respect to psi. As promised, we have Planck's constant in multiple places. We also have the mass of the object m and a double derivative with respect to the position. There is also a potential term v, which generally needs to be specified for a given problem, and then on the other side there is I, which is known as the imaginary number defined as I equal to the square root of minus 1, and finally we have the time derivative. Now let's address the elephant in the room. What is this psi? This is called the wave function, and it is a fundamental object in quantum mechanics used to describe the particle or object of interest. You might ask what the point of a wave function is. To answer this question, we must go back hundreds of years, as the trouble originates in the search of the correct description of light. At the time of Newton, it was clear that many things could be described as particles, but light showed to have wave-like properties. Especially after Thomas Young's double-slit experiment, light seemed as if it was like a wave. But then Planck came along with his idea of the quantized photon, which classically makes sense if you think of the photon as a particle. The problem essentially boils down to the wave-particle duality. In quantum mechanics, one can describe objects as waves or particles, at least on quantum scales. This leads us back to the concept of the wave function, which incorporates this concept that the object can have both particle and wave-like behavior. Thus, the classical idea of having either particles or waves is replaced by having a wave function which encompasses both concepts. It should be clear now that the wave function is an essential quantity in quantum mechanics. Going back to the Schrödinger equation, things should make more sense now. The reason why we have the wave function everywhere is that we are asking how the wave function is affected by change in position by a given potential and how it changes in time. As an example, we could consider the wave function of an electron and then figure out how the electron behaves according to this equation, and we will discuss more of that in a following video about atoms. This leads us to another way that quantum mechanics changed the world. The wave function is a probabilistic object, thus quantum mechanics itself is probabilistic, unlike classical physics, which is deterministic. This essentially means that at quantum level you don't know where a particle is. You can calculate the expected place to find like an electron, but it's just statistically the most likely position. In principle, it can be in other places. When we measure the position of some object, the wave function simply gives us a random value from the underlying probability. If we measure a lot of times, we will eventually see some wave-like pattern, and we will also see that some values are more common. At a classical level, we usually do not observe this, because these waves are so incredibly tiny that the wave just appears to be at one point. This brings us to the genius experiment by Thomas Young. He put up a background and then sent light into this background through two slits. Because light has this wave-like behavior, even on macro scales we can see this wave pattern on the background. Now if we just send one photon, what would happen? You would just have one dot and then you send another one. It will make a dot somewhere else. Then you continue this process and let many photons through, and slowly you will see this wave pattern emerge. The probabilistic behavior is simply encoded into the wave function of the photon. The crazy part is, if you put a detector on one of the slits to measure which slit the photon travels through, then the wave pattern disappears, and you just get two dots on your background where the photon hits, just like if they were particles. This is crazy. Just by observing the photon, we have changed its behavior. This double-slit experiment is very fascinating, and it highlights something essential about the world. There is a difference between the real world and the world we measure, because the act of measuring has an impact on the world. This leads us to the fact that some process can happen only when we do not observe the process. We will discuss such things later, and in the next video we will discuss the uncertainty principle, which is another thing that changed our understanding of physics forever. And on that note, let's finish the video, and as always I hope you learned something new. If you did, please like, comment and subscribe for more, and stay tuned.